Welcome again to our lecture course on the early universe. So we have three settings left. So what do I do today? Today I finish the Newtonian theory of perturbations and also start with the general relativistic treatment. And the next time will be the last lecture, and I will finish this general theory of perturbations and then go back to the inflationary universe to apply it to show you how the seeds of structure in the universe arise. This is a brief review here of the Newtonian theory. So we restrict to an ideal fluid and have the idea, of course, of having small perturbations around the homogeneous isotropic background. So we have here the parameters of the fluid, which is the density, which is a mass density in the Newtonian theory, the entropy density, the velocity of the perturbations, and of course we have the pressure, which we treat as a function of density and entropy density. Now, so far I discussed the static universe, which is the traditional field of Newtonian theory, because in those early times no one had thought about an expanding universe. So that's the classical Newtonian theory of gravitational perturbations, and it's also sometimes called gene theory because James Jeans developed many of the central equations. I don't write down all the equations again. You have just to go to my previous lecture. For example, for the adiabatic perturbations, which are characterized by vanishing entropy perturbations, I derived for rho in Fourier space, so it's characterized by the wave numbers. This rather simple equation, so d rho double dot plus something that we also call omega squared, d rho is equal 0. Now, the behavior depends, of course, on the solution depends on this here. So whether, this here dominates or where this dominates. You see here there's a minus sign, and this causes all the central features. So for very small wavelengths, actually for wavelengths that are smaller than these critical wavelengths, also called Jeans wavelengths, the first term dominates, so gravity is unimportant and we have more or less oscillations, so sound waves if you like. And the opposite case is when we are much bigger wavelengths than lambda j, then this term dominates, and because of that minus, we have exponentially increasing and exponentially decreasing solutions. Of course, the decreasing solutions we don't have to take care because they fade away, but of course the exponentially increasing solutions, they cause then the instability and the gravitational collapse. So that's I think the central structure of the equations. Of course, if you are non-adiabatic, you have these delta S's here. We also discussed that, but you have to keep in mind, these two options of the signs, and the scales are set by the Jeans wavelengths. Now, today, first I will now go to an expanding universe, but still use the Newtonian equations. That's not quite, historically correct. But it serves as a preparation for the Einsteinian case, which is more complicated, but of course where we have to deal with an expanding universe. So let us assume we have the Newtonian limit, but we are in an expanding universe. So we have a background described by the mass density rho naught of t. We also assume now, because we are in an expanding universe, we assume the validity of Hubble's law, as at least as an approximation in the limit we are interested in. So we call also V naught, because it refers to the background, is h of t times x. So this is Hubble. And then we have to address the equations which we have written down earlier, and the first is the continuum equation. And if you insert here the v here, right, then you get the following. So you get from this that rho naught dot plus 3h times rho naught is equals 0. So of course you have listened to the GR lecture courses, so perhaps you recall that in GR we have the equation that rho dot plus 3h, and we have also rho, but there is in addition the pressure here. So this pressure of course is negligible in Newtonian theory. Otherwise we have to deal with GR, because only in GR P gravitates. In Newtonian theory only the rho. So that's for the background. Now it's of advantage to use so-called co-moving coordinates, already known from relativity. So I use in the following a co-moving dimensionless coordinate or coordinates Q, I call, and they are defined by the following x. Okay, x is also a function of t here. I should write here down, but let me write it down here. And we put as the scale factor of the expansion out of it. No? So we have then here a timeless variable q. That's the co-moving coordinate. So you just somehow expand with the universe, and the expansion information is put in that scale factor. So that's important here. So co-moving coordinate q, often used then also in relativity. Now it's clear if we have this, that from this we get the velocity is okay, that's written down here, h of t x of t, but this is then a dot of t times q, because this is just a derivative of this, so a dot times q. So you get from this, of course, that h is a dot over a, as we anyway know from relativity. Now using the q, of course, then we have to rewrite also the derivatives from a coordinate system where x is fixed to coordinate system where q is fixed. No? So recall, I mean, just from standard calculus, if we have a function that depends on x and t, and we want to have this partial time derivative at a constant q, then we can rewrite it as a derivative for constant x, and then of course we have the chain rule. We have then the df over dxj times dxj over dt, because now x, I mean, is a of t times q, so you have here also a t derivative here, and this here is a dot qj, and of course it's our v naught j, so that we have here d over dt at a fixed x. No, so I bring this here to the other side, so I have then d over dt at a fixed q, and then of course we have this extra term which comes then with a minus sign, which has then a minus v naught times nabla x. Also the nabla x, of course, is then, because of that here, 1 over a the nabla q. Right, okay, I should have here. So we have to, or we want to rewrite the equations for the density perturbations in terms of this co-moving coordinate, which we did not need, of course, for the static universe. So let us define the relative density perturbation. Delta which of course is dimensionless, is the delta rho over rho naught. Just a number that gives you the size of that density perturbations. Now, from the perturbed hydrodynamic equations, I have given you last time, the equations in general, not only for the adiabatic case, but it's perhaps interesting here or sufficient to restrict to the adiabatic case. So we take those equations and just use this rewriting with respect to Q. No? And I leave this short calculation as an exercise, and you get the following. So from the perturbed hydrodynamic equations, one finds for the adiabatic case, otherwise you have these inhomogeneous terms, the following. So, and there will also be an extra term. So we find that an equation that is very similar to the original case of the static universe, but here we get a term 2h delta dot. It's a kind of friction term with the first derivative, which comes from this rewriting and brings the Hubble parameter into play. And then we have here minus cs squared over a squared nabla squared delta minus 4 pi g rho naught times delta equals 0. Now, so you see here, this is without the blue term corresponds to this equation. Well, this is in Fourier space, this is in ordinary space, so I should say this is also here with respect to Q. So this nabla is the Q nabla. So this is what, if you go to Fourier space, then replaces this one. And let me write it down in Fourier space. So we have here, the Fourier transform delta of x and t integral. So standard with this factor here, delta k of t e to the I k q. No? And this is also what we call just delta. Right, so yeah. Then we have from this here, this equation, that delta k double dot plus 2h delta k dot, and then plus cs squared k squared over a squared minus 4 pi g rho naught times delta k equals 0. Now, so you have to compare this equation with the static one. Okay, you see we have here this additional term, which brings all the new things into play for the expanding universe. I should also mention here the following. When here the k, which is the wave number, has a dimension 1 over length. That's what we usually have in a Euclidean case in static physics. Now here, this k actually is a dimensionless. I don't bother you with giving this a tilde or whatever. I think it's clear from the context. But so what was originally k squared and has a dimension now is a dimensionless k squared over the scale factor squared. So we also put out the dimension of the wave vector, right? So the standard k is then this new dimensionless k, which is just a fixed number, time independent, over the scale factor. I hope this is clear from the context, and I don't want to use here a new notation which no one uses. Yeah, so that also holds then for the gene's length. Well, the gene's length we define now as a 2 pi kj and times the scale factor. Yeah, so also here we put a scale here into this, and this is also a number. So that cs over pi g times rho naught, this is the same as before here, but the kj is here defined differently, and the difference is here in that scale factor. Now, so that's the co-moving wavelength, if you like, which is a fixed number, but dimensionless, and but which scales with a's of the universe. You have a fixed scale, and the universe expands, and then all these scales, they run with the scale factor. So maybe I write this down again so that it's clear. So here we have another definition: 2 square root of pi j rho naught over cs and times a. No, so here really we have here that a, which is here. And in cosmology texts, as I said, there usually the same symbols are used, whether it's co-moving k or not, and you have to see this from the context, and so that you do not confuse the one which is physical, which has a dimensions, and the other which is a kind of label of the mode. Right. Let us go to an example. Well, in Newtonian theory, that's maybe the only sensible example, because we don't have a pressure, and so we don't have radiation-dominated universe and the like. So we only have a flat matter-dominated universe. That's the Newtonian case. So if you have a flat matter-dominated universe, we have seen in the GR class that for that case the Friedmann equations more or less coincide with the Newtonian, with the equations of Newtonian cosmology. So we can use those equations. So we have h squared, Hubble squared, which is 8 pi g over 3 times rho naught. Now that's the Friedmann equation, but if we set the curvature parameter equal to 0, and if you have no pressure and of course no cosmological constant, then we have this Newtonian equation. And we know also that here a is proportional to t to the 2/3, because this here is 1 over a cube. So you get from this here that rho naught is, if you insert this here and use that it's 1 over a cube, it's 1 over 6 pi g times t squared. So we have from this then, for the gene's length, lambda g is pi square root of 6 times, and this is the central part, CST, the sound velocity of that density perturbation. This is what we call sound. You should not think too much about hearing music here. Sound just means the propagation of density perturbations. But it's a common name here also. So here, this here is called the sound horizon. Because this is as far with the sound velocity the perturbation could propagate in the time t, which is the age of the universe. And you see that the gene's length is proportional to the sound horizon. Gene's length is proportional to the sound horizon. Instead of the gene's length, astronomers also prefer sometimes to use the so-called gene's mass. Now that's, you can imagine, it's just if you have a length, then you have a length cube, which gives you a volume, and if you multiply this with the density, then you have a mass in that volume. So one can also use so the gene's mass. And the definition here, mj, is just density times lambda j cubed. Yeah. So you could add here some geometric factor for pi over 3, but this does not matter. Yeah. So here we had this equation, and this here, like in the static case, we call omega a small omega squared. Omega k squared, because this gives you an oscillator equation, okay, an oscillator with a damping term. And then you can use, of course, all your standard experience with these equations from mechanics. And it's not surprising that such equations emerge, because we have the restriction for small perturbations. No? So we had this, let me write it down again. So delta k double dot plus 2h delta k dot plus omega k squared delta k is equal to 0. Okay, then you could now start solving this equation, but it turns out useful also that this useful to have another variable so that this equation be simplified. No? So we use a new variable yk that is defined as, again, scale factor times delta k. Now, so the scale factor is, from its very name, it's used to shift the scales out or in equations. And here, why do we do that? When convince yourself, if you use this instead of that, then we absorb the first derivative term into the definition, and we only have a double dot and an undotted, which is simpler to deal with, but of course you have to, the difficulty then lies here in that you have to know, of course, then the behavior of A. Now, if you use that, and I think that every one of you can do that calculation, so we have then, we get the following: omega k squared minus a double dot over a yk is equals 0. No? So you have here, this is a of t, of course, and so time derivatives enter, and they enter in this way. Now let us insert what we had here for the omega k squared. So that's here what is written down here. And let us also use here this, or substitute this by using this equation here. And if you do that, just convince yourself that you get omega yk double dot, and then you have plus cs squared k squared over a squared minus 8 pi g over 3 rho naught. So there are some cancellations and you can combine terms, but you only need what is here on that blackboard. Yk equals 0. So you see, very nice. I mean, it looks like the old equation, but without the first derivative. We can also use the wavelengths and the genes wavelengths here to bring in. So we use this here, and generally the wavelength is 2 pi over k times a. So we can write this here as 4 pi squared cs squared 1 over lambda squared minus 2 over 3 lambda j squared. No? So I wrote it in this way with lambda j because, again, we compare two situations. I mean, a situation where lambda is much smaller and a situation where lambda is much bigger than lambda j. And the gene's length brings in the important scale, and either we are below, where gravity does not play a major role, or we are above, higher, then gravity is important. And so let us do this. So we have here the first situation, that lambda is much smaller than lambda j. And it's clear that then if this is lambda small, 1 over lambda squared is much larger. So we only need this term here. So we have here yk double dot plus 4 pi squared cs squared over lambda squared yk is equal to 0. Okay, lambda is a function of t. You should not forget that. But apart from that, it's an equation from the harmonic oscillator, like the harmonic oscillator. So the solutions are wave-like solutions. Okay, not exact waves because lambda is a function of t, but they are waves. So solutions are sound waves. If to write down explicitly, let us use the original version of this equation without the lambda, just the scale factor, which is omega k double dot plus cs squared k squared over a squared yk equals 0. Yeah, that's the same. It just neglect this term and have only this term, and we call this here, for simplicity, a capital omega squared, just to give it a name. Now, of course, you can solve this when you have a of t here inserted, but it's sufficient for us to solve it in the case when if this is only slowly varying. So if omega dot is small, so the solution for omega dot much smaller than omega squared, then you have, it's sometimes called WKB solution. This, of course, refers to quantum mechanics, but from the equations, it's the same structure. Yeah, so you can convince yourself that the approximate solution of this is proportional to square root of a over cs times e to the plus or minus I k, and then we have this integral d or cs dt over a of t. That's the approximate solution. Of course, if this were just constant, then you come back to the old situation. Then there's no expansion. And so if we go back to the original delta, so let me just write it here. There's also some space left. Delta k of t is proportional to 1 over square root of cs times a. So it's only the difference in the prefactor. And of course we have e to the plus or minus I k integral cs dt over a of t. So that is then the solution for the dimensionless density perturbation for very small wavelengths. And you see here we have this decrease with 1 over square root of a, and this comes originally from this additional term. Now, so you don't have this in the static case, but this friction term somehow leads here to that 1 over square root of a decrease. Okay, so far for the small wavelengths. What follows for the bigger wavelengths? So we have here then b is lambda much bigger than lambda j. Of course, for the general case, you can always solve it numerically if you like, and just set in the a squared exact expression. That's also not complicated, but it's here illustrative to see the limiting cases. So we have here then delta k double dot plus 2h delta k dot minus 4 pi g times rho naught times delta k equals 0. Now we have domination of that second gravitational term, the gravitational term. Here you see then this dominates over that. So this dominates over that. Gravity dominates over this, small wavelengths. And yeah, you can solve this, and one can find actually the following general solution. Just convince yourself that this is really the solution. Is then, of course, the second order equation has two integration constants, which I call C1 and C2. So C1 times Hubble times dt over A times h squared plus C2. Well, this is actually then just a Hubble parameter. And if we insert here that A of t is proportional to t to the 2/3, then we get here, okay, there are some other constants, but let's call it C1 tilde times t to the 2/3 plus another constant t2 tilde times 1 over t. So that would be the solution of this equation for very large wavelengths. And you see we have two contributions. One is a decaying solution with 1 over t, and one is an expanding or growing solution. And you see here that if this is negligible, that delta then grows with A. So the density perturbations, they themselves grow with the scale factor and the same power. So this is important. This is now really different from the static case. Recall, in the static case, we had just the e to the plus something t and e to the minus something. So they were exponential. Now in the expanding universe, the growth is no longer exponential. Yeah, we only have a power law increase. So it's a smaller increase. So that's due to the expansion of the universe somehow prevents this collapse to be exponential. So we have here no exponential increase, as in the static case. But or I should write down only power law increase. I can already mention here an issue that will, of course, become relevant in general relativity, which is the correct theory of the expanding universe. Today, of course, we have galaxies and structures, so definitely, delta, the density contrast today, is bigger than 1, because there is no longer, small perturbations. Our galaxy is not a small perturbation. So if we, and this is of course information from GR and from cosmology, if we have the cosmic microwave background, and we have these perturbations there, which are of order 10 to the minus 5. Yeah, so you would need at least a growth of 10 to the 5 to get from 10 to the minus 5 to 1. But the redshift of the CMB, that's correspond to about 1000, and you know that the ratio of the scale factors is given by the redshift. So we get from the time of recombination up to here only a growth of the factor 1000, which does not bring you from 10 to the minus 5 to 1. So let me only mention this, that the solution of this discrepancy, and in GR we get similar results, as you will see. We need cold dark matter. No? So CDM, which is cold dark matter, Now, this is not electromagnetically coupled to charges and photons. So as soon as the radiation-dominated phase is over, so all of this is GR knowledge, of course, which is A bigger than this A equilibrium, inhomogeneities can develop, but only for cold dark matter, because for the baryons they have to wait for the recombination, which is much later. This is what you see in the CMB, is from the recombination they have to be liberated first from the photons, but cold dark matter is not interacting with photons. So what can happen is that very early on already, at the start of the matter-dominated phase, the CDM, the cold dark matter, can form inhomogeneities. And then when recombination happens, the baryon can already, be attracted by that. So there's already a seed of an inhomogeneity. Well, I say this already now because we are dealing all in all with general relativity, and this was just meant to have a certain limiting case. So cold dark matter, so inhomogeneities can develop already for A bigger roughly than A EQ. No? They cannot develop in the radiation-dominated phase, but then, so before recombination. And so allows, baryons to develop sufficient inhomogeneities after recombination. So I don't write all the details now. It's clear we have this factor of 1000 only from the CMB to today. But the size is 10 to the minus 5 of the CMB fluctuation. So we need an extra factor, and we don't have time enough if everything were smooth up to recombination and only then start development. So we need some inhomogeneities earlier, and this is why we think that there is cold dark matter. It's not just because of the rotation curves that today we observe from the galaxies. That's also an independent, of course, hint. But this is even more important because otherwise our picture is inconsistent. I did not I don't want to mention again the vector perturbations. I did it briefly mention in the static case. They turn out, if one looks at them, to be irrelevant. So we have the vector perturbations. Perturbations in the velocity. So, and dvk turns out to be 1 over a times unit vector that is proportional to the direction of propagation, as in the static case, but we have here this extra 1 over a. So you see they decay. This means that they will not be relevant. They would only be relevant if initially you had very big ones. But if you initially had very big ones, that would be in conflict with the isotropy of the universe, because if you have a certain velocity perturbation, this gives you a direction, a distinguished direction, which we don't see. Even, if you go back to nucleosynthesis, everything is consistent with isotropy. No? So we don't think that they were very big early on, and if they were not very big early on and were small, they would even become smaller. So this is why we, and also most literature, don't talk about vector perturbations, and we can restrict here to the scalar perturbations. So after having finished perturbation theory for the Newtonian case, for the real Newtonian case with a static universe, and also for the Newtonian case if applied to an expanding pressureless universe, we now move to the real thing. namely discussing gravitational instability in GR, but you will see that many of the earlier features will also occur here, but as you know from GR, with more complicated equations and also some more complicated concepts. And the main problem that we encounter here is the problem of the coordinate freedom in GR, which was not the case with Newtonian theory with absolute space and absolute time. So if we have linear perturbations and we change coordinate systems, how can we avoid to get, say, coordinate artifacts? So the problem here, or the main problem, is the coordinate freedom. Here also called gauge freedom. Now, you recall from the discussion, or our earlier discussion, of weak gravitational waves, which is within linearized gravity. Also there, because of similarity with electrodynamics, people like to call it gauge freedom. Although, I mean, the full GR, the situation is different compared to gauge theories. So this is used synonymous. Coordinate freedom at the linearized level are gauge freedom. In the description of linear perturbations, so there's this danger of coordinate artifacts. Danger of coordinate artifacts, also called fictitious modes, I mean, which are not really there. So what do I mean here? Consider the following example. We have a homogeneous and isotropic universe where we have a row of x and t is just a function of t, like our old Friedmann universes. So we can have the standard foliation, so t and x, and so here we have this hypersurface of equal time t. So this here corresponds to t equals constant, and rho is also equal constant on the various slices. It depends on t, but on each slice, I should write on each slice, it is constant. Now, of course, you are free in GR to go to another coordinate system, because you have learned we have covariance, and we can use whatever coordinates we like. So we can here perturb this a little bit here, and this here maybe other way, and here like that, whatever you like. For some reason, then you choose this blue slices, and they correspond to, say, t tilde equals constant. But it's clear that on this blue slices, rho is no longer a constant. So rho tilde is no longer a constant. Okay, so if we have here, say, then we have here these perturbations that we call, for first it's the coordinate delta t of x and t. We can calculate in the following fictitious perturbations. So we have here, I mean, our old row of t. We can write now with respect to t tilde, so this is t tilde minus delta t of x and t. So you have a delta t everywhere. It depends on x and t. And the t is that's the same function, but now written with respect to a different t. And so if we expand that, when this is a small quantity, assume this is small, then this is approximately rho of t tilde minus the rho over dt at a time t tilde times delta t. So we can write this as rho of t tilde minus some delta rho of x and t. Now, this you can call a density perturbation, but is it really a perturbation? We know we have a homogeneous universe, so the density is constant everywhere. So you see here, this is just a pure coordinate artifact. By rewriting it with respect to t tilde. I mean, this rho is the same function as is, but it's if you write it with respect to this artificial blue time coordinate, then as a compensation, you get this coordinate perturbation. No? So that is here coordinate artifact. So if you do that, then you can do very long calculations with very complicated equations, and in the end you get results that have no meaning and are senseless because they are just artificial perturbations of coordinates and not what you observe in the universe. Now you could even do it the other way. I mean, if you have real perturbations, by a appropriate choice of coordinates, you can make them vanish. If you, for example, use hypersurface of constant energy density, right, maybe very strange hypersurfaces, then there's no perturbation. So you could even make vanish a real perturbation. These are big dangers. So the only way actually to circumvent this is to use so-called gauge invariant variables. Of course, this is not always possible, but you should have a formalism of gauge invariant variables so that if you go to a particular gauge, that it's under control. And that's what we also do in electrodynamics. We go for the vector potential to particular gauges, of course, but we have this under control. So use gauge invariant variables. Now that's the idea that we have, and I sketch to you how this is achieved, and write to you a set finally of gauge invariant variables which are used in the perturbed field equations. Okay, so let us become more concrete. So let us make the following ansatz for the space-time metric. Let us make the ansatz that it's given by the Robertson-Walker line element plus small metric perturbations. So we have here the following notation. So g mu nu 0 plus delta g mu nu of x. And so we have dx mu dx nu, and we take these to be dimensionless and put the dimensions here in this, the length dimension. So that's the Robertson-Walker metric. And for simplicity, we treat only the case of a flat spatial universe. That's what most people do, because observations seem to favor it, although it's not clear that that it's really flat exactly. So with here, so that's only our ansatz, k equals 0. And in this, so this gives us also a choice of coordinates, and in these coordinates we demand that these perturbations are much smaller than the background. You know this from the discussion of weak gravitational waves when you also make a similar ansatz. So we can write this as ds naught squared. So that's what we discussed in the first part of the lecture, and then the perturbation part. So this here, recall, is a standard line element. So it's a g mu nu 0 dx mu dx nu, and if we use conformal time, dt is a d eta, then we have here that we have a squared of eta minus d eta squared plus dx squared. I mean, the flat case, of course, we have the flat spatial part here, and here, sorry, this flat spatial part. We also have then the time part, and we have the scale factor. And in the following, as before, a prime denotes the derivative with respect to eta. Now comes an important step. So the perturbations here, they are classified by making use of the symmetries of the background. The symmetries of the background, because it's a flat space, we have, of course, spatial translations and spatial rotations. Of course, if you have a closed universe, then you no longer have these translations. You have other symmetries or restricted symmetries, but that's what we use here. No? So we classify the perturbations delta G mu nu of xi by the symmetries of the background. No, so that's for the time being at a fixed time. So which is for k equals 0 are the spatial translations and rotations. So there is some notation involved in that. I mean, these perturbations, because they're perturbations of the space-time matrix, you have 10 functions, because G mu nu has 10 entries, but we write in such a way that we have 10, well, actually that we have scalars, vectors, and tensors that all in all add up to 10 degrees of freedom. You will see how this goes. So we write first delta G 0, 0. Now, because time and space are here, I mean, somehow separated, we also, this is reflected here also in the notation for the delta G. So delta G 0, 0, we make the following minus 2a squared. So we extract the scale factor squared and define a phi, which is actually this similar to the Newtonian or analogous to the Newtonian potential. Yeah, okay. I'm not sure that every author has here a minus 2, but certainly a squared phi. So that's a scalar under rotations. Yeah, and this is a three-dimensional scalar, so it's analogous to the Newtonian potential. Then we have the delta G0a, which defines two further functions. Okay, scale factor is separate, and then we have here a derivative part and just another part. But this other part with a covector here means that that is we demand it to be divergence free, the corresponding vector. Because these are spatial indices and because the spatial metric is flat, raising and lowering of indices is just done by the Kronecker, which you can just do. It's not so spatial index movement is done by delta AB, or its inverse. So that corresponds to what you know, of course, from calculus as a decomposition of a vector field into its curl-free and divergence part. So this is divergence-free, and this here is curl-free. So if we keep track of the function, so here we have one function here, right? And here we have also one function. Here we have in principle 3, but we have one condition. So this gives 3 minus 1, which is then in fact 2. And then comes the purely spatial part. That is naturally then a bit longer, because this is 1 plus 1 plus 2 is 4, so we have 6 other degrees of freedom that we have to bring in the notation, so which is a squared again. This is put in front, and then we have minus psi delta AB plus 2 d squared E over dxa dxb plus df a over dxb plus df b over dxa plus a tensorial part HAB. So here. Okay, so this is 1 degree of freedom here, a scalar also. Then we have here the second derivative. Okay, this refers to that. So this here would be 1 degree of freedom. Now here we have a further restriction. So this is with again vanishing divergence. Now, so you have 3 in principle, F1, F2, F3, but with one condition gives 2. And then here, of course, because we have put out these parts, we can use this HAB as we did in the discussion of gravitational waves in the so-called transverse traceless gauge. So here we have here the TT gauge as in relativity 1, which means that it's traceless and that it's transverse, so vanishing divergence, because the divergence has been put here, right, in these other terms, and the traces here. Now you see here, this is in that term. So that means we are left here with 2. And this you know from our earlier discussion here, and you can count. I mean, these are 2. So all in all, if you count, then we have here 1 plus 1 plus 2 plus 1 plus 1 plus 2 plus 2, we have 10. No? So 10 metric components. Yeah. Which is just now at this point a rewriting, but a rewriting, okay, with a certain aim in mind. I mean, using the symmetries here of the background, and also these various parts have different physical interpretation. Okay, let me collect these various parts. So we have so-called scalar perturbations, so-called vector perturbations, and so-called tensor perturbations. So we have scalar perturbations. They are the function phi, psi, b, and e. Then we have the vector perturbations. These are the SA and FA, or they are vector instead of co-vector components, so they are divergence free. And then we have the tensor perturbations, which are the transversal traceless HAB. Now, these vector perturbations, as in Newtonian theory, if you do the calculations, and I have no time to do that here, they also decay. So these are 4, but they decay rapidly, and are therefore negligible. Not for similar reasons as in Newtonian theory. Then, of course, we have to deal with these 4. And they are induced actually by the energy perturbations, and they are really important for the structure formation. So induced by energy perturbations, and so important for structure formation. And of course, these are old friends. You know already these are described gravitational waves. So these are 2, so that all in all we have 10, and these describe gravitational waves. An important fact is the following, that these 3 types of perturbations, scalar, vector, and tensor, in the linear approximation that we deal with here, they decouple. And this is why they can be treated separately. This is no longer true in general. If you go to higher orders, then you, of course, the theory is non-linear. You have couplings between all of them. This is, of course, very complicated. But fortunately for the early universe, because the fluctuations are very small, we can neglect this. It's important for later processes of galaxy formation, but not for what we are interested in. No? So an important fact is that these 3 types of perturbations are in the linear approximation decoupled, no, and can be treated separately, no, in this linear approximation. Now the final thing for today is just to mention the following, and we will do the calculation the next time. So what we do here actually is then to have a coordinate transformation x mu going to x mu tilde, x mu plus xi mu of x, with xi mu small, and consider the transformation of the metric perturbations under this. No? So of course, from your knowledge of GR, you know, how the metric transforms, and the metric transforms to a G mu tilde. That is delta G mu nu, and if we evaluate this at the same coordinate value, then the difference is the Lie derivative with respect to G0 mu nu. And if you look back to your old notes or you do the calculations, then we have delta G mu nu minus 0 G mu nu comma alpha psi alpha minus G alpha nu 0 xi comma mu alpha minus G mu alpha 0 psi alpha. Okay, lengthy terms, but you know these lengthy terms from your lecture course. So the xi mu here, this difference in the coordinates, we of course have to divide this up into the temporal and the spatial part, because we have everything decomposed into space and time components, and we've also introduced the notation that that the spatial part we write as a curl-free and as a divergence-free part. So this is curl-free because it's a divergence, and this has this is of course a divergence-free. It's transversal, and so from this we can then inserting this here, then we get explicit expressions for the various components here, the delta G00, the delta dG0A, and dGAB. Let me just write it down. Recall that we had 0 G00 is minus a squared of eta, and 0 GAB is a squared of eta delta AB. So and with that we have delta tilde g00, which we call minus 2a squared phi tilde is delta g00, and this is minus 2a squared phi plus 2a psi 0 prime. The derivatives with respect to the conformal time. This is what you get from this here, and delta g0a tilde is dg0a plus a squared, and then you have psi prime orthogonal a plus theta prime minus psi 0 comma a, and finally the space part, we have delta gab tilde is delta gab plus a squared 2a prime over a delta ab psi 0 plus 2 theta comma ab plus psi orthogonal a comma b plus psi orthogonal b comma a. No, I mean here the index position does not matter, as I said. Okay, so the final message from this is that if you use then again, I mean, for the original ones, the definitions here is already there. No? So you see here the transformation of phi, no, from phi to phi tilde. That if you use, I mean, these perturbations, both for the originals untilted and for the new one tilted, then you get transformations for these 10 quantities. No? So from this here, so transformation equations for phi, psi, etc. Okay, that's as far as we want to I want to go today. So next time, which will be the last lecture course, I will write down these transformation equations after brief review, and I will then form a gauge invariant combination, so-called Bardeen potentials, and in them I will then discuss the perturbation equations. So you see that the case of GR is much more involved, as expected, that we have to take care, I mean, for I mean, the calculations and how we interpret the quantities. But so far, I can say that everything is under control, and I will discuss the details then next time. So bye-bye for today, and until next time.